Today we are going to study current electricity. Current electricity. In order to understand this chapter, first you need to understand the concept of charge. So first you need to understand the concept of charge. What do we know about charges? We know that charges are of two types. Charges are of two types. What are the two types of charges? Positive charge and negative charge. Positive charge and negative charge. Now the question arises how these charges are developed. The question arises how these charges are developed. How these charges are developed. Now, charges are developed by transfer of electrons. Charges are developed by transfer of electrons. Transfer of electrons. Now, how these electrons transfer? What is the procedure? The procedure is when we rub two bodies against each other, there takes place a transfer of electrons. So, what we can say, by rubbing two bodies against each other. Okay, what happens when we rub two bodies against each other? When we rub two bodies against each other, one body loses electron while the other gains electron. So, one body gains electron while the other body loses electron. The body which gains electron, it has an excess of electrons. And hence these are negatively charged bodies. Okay, and the one that loses electrons, they have deficiency of electrons. And they become positively charged. Okay, now there are few things which we should know about charges. What are those things? Number one. Like charges repel, unlike charges attract. Like charges repel while unlike charges attract. Apart from this, what else? The other point is how to designate this charge. How do you write this charge on a body? So this charge on a body is denoted by a symbol Q. Charge on a body is denoted by symbol Q. Okay, you can also write capital Q. There's no harm. You can write capital Q or small q, but whatever you're choosing to write, it should be throughout. Okay, now another important thing, what is the unit of charge? Unit of charge. What is the unit of charge? The SI unit of charge, The SI unit of charge is coulomb. Is coulomb. C-O-U-L-O-M-B, coulomb, and we write it as capital C. Okay, so this is all about charges. Now if you want to calculate the total charge on a body, how you are going to calculate that? So let us see how do we calculate the total charge on a body. Okay, suppose there is a body and there are n number of electrons in that body. How many number of electrons? N. Let n be the number of electrons in a body. Okay, and we know that the charge on each electron is denoted by symbol E. So let E be the charge on each electron. N is the number of electron and E is the charge on each electron. Therefore, total charge, which we denote by the symbol Q, will be equal to N into E. Number of electrons into charge on each electrons. And it will be plus minus Ne, because we know if it is positively charged then plus Ne, if it is negatively charged then minus Ne. Okay, one more thing, charge on each electron, it has a value. What is that value? The value is equal to minus 1.6 into 10 to the power minus 19 coulomb. So the charge on each electron is known. Now let us do a question. Okay, for example, let us take an example of a question. If the question says how many electrons are there in 1 coulomb charge, how many electrons are there in 1 coulomb charge? So how are we going to find this? See, we have two approaches for this solution. One is using the formula and the other is by unitary method. Okay, I'll show you both the ways. Let's see first how we do it with the help of a formula. Formula is known to us. If we want to find the number of electrons, how we are going to use this formula. We know what are the data given. First, write the data. Q is 1 coulomb. And we know that charge on each electron E is equal to 1.6 into 10 to the power minus 19 coulomb. Okay, so according to the formula, Q is equal to N into E, and here we want to find N. So let us make N the subject of formula. So this becomes Q by E. Q is 1 and E is 1.6 into 10 to the power minus 19. If you calculate this, you are going to get 6.25 into 10 to the power 18 electrons. The same thing you can do it by unitary method. Well, how you are going to do that? I'm going to show you how we will do it using unitary method. We know that 1.6 into 10 to the power minus 19 coulomb means how many electron? 1 electron. Okay, this much charge is 1 electron. Therefore, if we have 1 coulomb charge, then how many electron it has to be? 1 by 1.6 into 10 to the power minus 19, which is equal to 6.25 into 10 to the power 18 electrons. So this is how we are going to solve such questions. This was all about charges. Now let us see what is current. Okay, you have understood charge. Now let us see what is current. Let us start with the definition of current. What is the definition of current? The definition of current is defined as the rate of flow of charge. Current is defined as the rate of flow of charge. Okay, rate of flow of charge. Now, what is rate of flow? Always remember, with anything, if you divide it with time, any physical quantity, if you divide it with time, the term rate is added to it. So here we have charge divided by time. So rate of flow of charge. So how you can write it? As a mathematical statement, I, that is current. Current is denoted by the symbol I. I is equal to Q by T. Okay. I is equal to Q by T, where I is current, Q is charge, and T is time. Okay, so here we have the formula for current. Now what will be the unit of current? Unit of current. From the formula itself, you can derive the unit for current. Okay, so basically, the current, the SI unit of current is ampere. SI unit of current is ampere. A-M-P-E-R-E. It is denoted by the symbol capital A. So SI unit of current is ampere. So how I am going to establish it? With the help of the formula. 1 ampere is equal to, for charge, 1 coulomb by 1 second. So you can also write it as 1 coulomb per second, or 1 coulomb second inverse. Okay, so coulomb per second is also the SI unit of current, which we write it as ampere. Okay, there are few other units also apart from the SI unit, some smaller units. What are those units? Like milliampere. Milliampere. Okay, another small unit is microampere. Okay, now how do you relate milliampere with ampere or microampere with ampere? 1 milliampere is equal to 10 to the power minus 3 ampere. Similarly, 1 microampere is equal to 10 to the power minus 6 ampere. Is it clear? Okay, now suppose there are n number of electrons and each electron has charge E. So we have already discussed that if there are n number of electrons and each electron has charge E, then Q is equal to Ne. Now Q is equal to Ne, then from the formula of current, what do we have? I is equal to Q by T. Okay, so we can write it as, in the place of Q we can write Ne by T. Okay, so we got another formula. Okay, so let us do a sum on this formula. Let's see a question. Okay, the question says that suppose the number of electrons n, is equal to 6.25 into 10 to the power 16 electrons. How many electrons? 6.25 into 10 to the power 16 electrons. Okay, these number of electrons are flowing from A to B in time 2 seconds. In time T is equal to 2 seconds. Okay, we need to find the current I, and we know the charge on each electron E is equal to 1.6 into 10 to the power minus 19 coulomb. Okay, so let us find I. We have the formula for I. What is the formula for I? I is equal to Q by T, which we can write it as NE by T. We have the values of N. N is 6.25 into 10 to the power 16. We have E, which is 1.6 into 10 to the power minus 19. And we have time as 2 seconds. Okay, if we do the calculations, so let us do the calculations. Okay, so you see, after doing the calculations, you are going to get it as 5 into 10 to the power minus 3 ampere. Okay, we know that 10 to the power minus 3 ampere is equal to 1 milliampere. So we can also write it as 5 milliampere. You can leave the answer to ampere. You can convert it to milliampere, not an issue. Okay. Another question can be here is, if the number of electrons are flowing from A to B, what will be the direction of flow of current? What will be the direction of flow of current? Always remember, if the electrons flow from A to B, the current will flow from B to A. So from B to A, this is the direction of flow of current. Current flows always opposite to the direction of flow of electrons. I hope the question is clear to you. Okay, now we are going to understand the concept of potential and potential difference. To understand this concept, first we need to see their definition. So let us see the definition of potential and potential difference. Okay, first let us see the definition for potential. What is the definition of potential? It says that the potential at a point is defined as the amount of work done in bringing unit positive charge from infinity to that point. So basically potential is of a point, and if you want the potential of a point, what you need to do, you need to bring a positive charge from infinity to that point. So the work done in doing this will be the measure of potential. So let us understand this in detail. This is the definition. So let us see. Suppose there's a positive charge here. Okay. And you want to find the potential at this point due to this charge. Let us name this point. Point A, you want to find the potential at point A due to this positive charge. Okay. To understand or to find out, to calculate, to know the potential of point A due to this positive charge, what you need to do, you need to have a test charge which is at infinity. So suppose this is infinity and you have a test charge Q at infinity. Okay, what you are doing, you are bringing this test charge Q to this point A. Okay, the work done in bringing this test charge Q from infinity to this point A will be the measure of potential. Now you'll say, ma'am, why there will be a work done in bringing this test charge Q from infinity to this point A? You see there's a positive charge here. Suppose there's a negative charge here. What will happen, be it positive or negative, if I'm trying to bring a test charge which is by default always positive, there will be a force exerted on this charge. If a positive charge is placed here, then there will be a repulsive force on this test charge. If a negative charge is placed at this point, then there will be an attractive force on this test charge Q. So there will be a force, and when we are bringing this charge Q from infinity to this point, so there's a displacement as well. There's a force and there's a displacement, so there will be work done. So what we say about potential, it is denoted by a letter V. V is equal to work done in bringing a test charge Q from infinity to this point A. Clear? So what we get the formula for potential, V is equal to W by Q. Okay. Now coming to the definition of potential difference. Okay, what is potential difference? The potential difference PD between 2 points. Now here we have 2 points, here we had 1 point. Okay, here we have 2 points. Between 2 points is equal to the work done in moving a unit positive charge from one point to the other point. That means here we don't have infinity. Okay, we have 2 points. for which we need to find the potential difference. So first let us consider 2 points, A and point B. Okay, you want to carry a test charge, or you want to bring a test charge Q from A to B. In doing so, the work done will be the measure of the potential difference. So suppose the potential at this point is VA, the potential at this point is VB. So potential difference in carrying a test charge Q from A to B will be written as VA minus VB, and according to the definition it is equal to the work done in moving a unit positive charge from one point to another point. Work done in moving a unit positive charge from one point to the other point. So VA minus VB is equal to W by Q. Okay, now coming to the unit. What is the unit? Unit of potential. The SI unit of potential is volt. Okay, we denote it with the symbol V. This is the SI unit of potential. And same goes for potential difference. Even potential difference has the unit volt. Now, how we can write it? We can place it in this formula. We can write it as 1 volt is equal to 1 joule by 1 coulomb. That means the work done in carrying 1 coulomb of charge from infinity to a point P is 1 joule, and hence it is given or said as 1 volt. So what is 1 volt? If anybody asks you the definition of 1 volt, how you are going to define 1 volt? 1 volt is equal to the work done that is 1 joule in carrying per unit charge, that is 1 coulomb of charge from infinity to that point. So you can write it as 1 joule per coulomb, or 1 joule coulomb inverse. Okay, 1 joule per coulomb is equal to 1 volt. Okay, now why are we studying this potential and potential difference? So the question arises here is, what is the significance of potential and potential difference? To understand the significance, I will deviate a little from the topic. Okay, let us go to the topic of heat. Okay, or basically I would say temperature. We all know what is temperature. Temperature is the degree of hotness or coldness of a body. This is the definition of temperature, degree of hotness or coldness of a body. Now suppose there are two bodies, body A and B, and the temperature of the two bodies are given to you. Suppose this is at 100 degrees C and this is at 60 degrees C. Now if a person asks you from where to where the heat will flow flow from B to A, or it will flow from A to B? You can easily say, by the help of temperature, you can easily say that heat will flow from A to B, because we know that heat flows from a higher temperature to a lower temperature. Heat flows from a hotter body to a colder body. So with the help of this temperature, number one, you can determine the direction of flow of heat. Number one. Number two, if there is a temperature difference between the two bodies. This is 100 degree, this is 60 degree. So what is the temperature difference? 40. So there is a temperature difference between the two bodies, and hence that is why we are having a flow of heat here. Suppose this body is at the same temperature as body A, 100 degrees C. Then in that case, what would happen? There will be no flow of heat. No flow of heat. Okay, there will be no flow of heat. Now coming back to my topic, just as when there was no temperature difference, we did not have any flow of heat. Similarly, if there is no potential difference between two bodies, if there is no potential difference between 2 points, 2 terminals, then current will not flow. then current will not flow. So the flow of current will always require a potential difference. Now how does this current flow? The current flow from a higher potential to a lower potential. Let me explain you with the help of a circuit. Suppose you have a wire, okay? I name that wire as AB. Okay, this wire is not connected to any battery. Okay, so at this particular time there is no current flowing in this wire, no current flowing in this wire. Why? Because they don't have any potential difference across its terminal. Now I'm connecting this wire to a battery. Okay, this is the symbol of a battery. The bigger terminal is a positive terminal and the smaller arm is the negative terminal. So I am applying a higher potential at end A and a lower potential at end B. Okay, so there exists a potential difference now across the end A and B. Now since there is a potential difference across the ends A and B, current will start flowing from higher potential to lower potential. Okay, the concept is clear. The current will flow from higher potential to lower potential. When there was no potential difference, when there was no cell attached to the wire AB, there was no current flowing in the wire. So this is why we study potential and potential difference in current electricity. Now let us see what is resistance. Let us understand the concept of resistance. Resistance is an English term. Okay, what does basically resistance mean? Resistance means an obstruction. If you see it in an English dictionary, resistance means an obstruction, and hence the same definition goes to in physics as well. Okay, so how do we define resistance in physics or in current electricity? It is the obstruction offered to the flow of current. The obstruction offered to the flow of current. Okay, now who will offer this obstruction? By the conductor. By the conductor. Conductor, we know there's a good conductor, bad conductor, insulator, be it any metal, be it silver, which is the best conductor of electricity, or be it other conductors of electricity. Every conductor is going to offer some amount of resistance. If it's a very good conductor, it is going to offer less resistance. If it is not very good conductor, it is going to offer a little more resistance. But irrespective of that, resistance will exist in conductors. Okay, so resistance exists in conductors. So we should know what is the cause of resistance. So let us understand the cause of resistance. What is the cause? Okay. To understand the cause of resistance, let us take cross section of a wire. Let us take cross section of a wire. I'm taking a big cross section of a wire. Okay, or a conductor. So in this conducting wire, what do we have? Any metal has a large number of electrons and an equal number of positive ions. Okay, what do they have? They have an equal number of positive ions and a large number of electrons. Okay, these positive ions are fixed. Okay, whereas the electrons, they are free to move. And hence these electrons are called, since they are free to move, they are called free electrons. Okay. Now, these are free electrons. Now, what happens when we do not connect it with a battery? That means when there is no potential difference applied, when no potential difference is applied. I'm writing in short PD, potential difference. Okay, when no potential difference is applied across the ends of the conductors, these electrons move in a random manner, in a random fashion, wherever they feel like. Okay, they are free to move actually. So they move in a random fashion. When they are moving in a random manner, what are they doing? They are colliding among themselves and also with the positive ions. As you can see in the figure, they are colliding among themselves and with the positive ions. Now let us connect this conductor or the cross section of the conductor with a battery or a cell. That means we are going to apply a potential difference across its ends. Okay, so I'm connecting it to a battery or a cell. When I connect it to a cell, what I'm doing, I'm giving a positive terminal, higher potential to this one, and negative or a lower potential to the other end. When we give a potential, then what happens? A potential difference is established across the ends of the metal wire, and the electrons inside it starts moving in a straight line. Okay, they start moving from one end to the other end. From where to where? From negative terminal to positive terminal. So first let us draw the positive ions and the electrons to show the direction of flow of electrons. Okay, electrons, dotted ones are the electrons. Okay, now what is happening? Because of this potential difference across the ends of the metal wire or because of the conductor, the electrons start moving from negative terminal to positive terminal. They are getting accelerated. The potential difference is providing them an acceleration. They are getting accelerated towards the positive terminal. Okay, but during they are getting accelerated, then definitely they are gaining some speed. Their speed is increasing, but during their movement, what do? They collide with the fixed positive ions and they lose some of their kinetic energy. Now since they are losing their kinetic energy, what is happening to the speed of the electrons? The speed of the electron is decreasing. So after the collision, what is happening? The speed is decreasing. Again, because of the existing potential difference, because we have given a cell which is constantly providing a potential difference to the metal wire, what is happening? Again, the electrons are getting accelerated and again the speed increases, and then again in collision with the positive ion, their speed decreases. So what happens? This process continues. The increase and decrease in speed continues to occur. Okay, now when this continues to occur, what happens? As a result, the electrons do not move in bulk. With a continuously increasing speed. What do? They drift. So there is a drift, but there is a drift. Drift of what? Drift of electrons. Where? Towards the positive terminal. Okay, clear? Because of this increasing and decreasing speed, there is a drift of electrons towards the positive terminal. So what is happening? Thus a metal wire offers some resistance to the flow of electrons. Conclusion: thus a metal wire offers resistance to the flow of electrons. Okay, And this resistance depends on what? It depends on the number of collisions suffered by the electrons. Okay, it depends on the resistance. It depends on the number of collision. Depends on the number of collisions suffered by the electrons. Okay, so this was all about resistance. In our next video, we will continue with Ohm's law. Till now in current electricity, we have learned the concept of charge, current, potential difference, potential and resistance. Now let us see what is Ohm's law. Ohm's law, basically there was a German scientist by this name. In 1826, he found a relationship between potential difference and current. And he established this relationship and laid it down in the form of a statement which is called Ohm's law. Now let us see what the statement says. According to Ohm's law, the current flowing in a conductor is directly proportional to the potential difference applied across its end, provided the physical conditions and temperature of the conductor remains constant. So what is Ohm's law saying about the relationship of potential difference and current? That they are directly proportional to each other, only provided if the physical conditions and the temperature of the conductor remains constant. So this is the statement. How we will write it in a mathematical form? Mathematically, we'll just write it as what it says, that the current is directly proportional to potential difference. So we know that the potential difference is designated by the letter V. So potential difference is directly proportional to the current I. Okay, now whenever we remove a proportionality sign with an whenever we replace a proportionality sign with an equal to sign, a constant comes. So let us replace this proportional sign with an equal to sign. So we will get a constant here on the right hand side. Now if I bring this current to the left hand side, what do we get? We get V by I is equal to constant. Okay, and this constant is equal to the resistance of the conductor. It was found experimentally that it is equal to the resistance of the conductor. Okay, so what we can write? V by I is equal to R. So this is a formula for Ohm's law. You can also write the same equation as V. Take I to the right hand side. So V is equal to IR. Okay. Now if suppose you have the current I is equal to 1. If the current is equal to 1, then we can say that resistance is mathematically equal to the potential difference. So what statement you can write from here? You can write that the resistance of a conductor is numerically equal to 1 is numerically equal to the potential difference across its ends when unit current flows through it. Okay, so let us write that statement. Thus what we can say, thus the resistance of a conductor is numerically equal to potential difference across its ends when unit current flows through it. Okay, now let us see, we have discussed about resistance, but we haven't discussed about the SI unit of resistance. So let us see what is the unit of resistances are. So unit of resistance. Okay, we will get the unit of resistance from this formula. So what we can write, R is equal to V by I. So unit of R will be equal to unit of V by unit of I. So what is the unit of V? Unit of V by unit of I. So unit of V is volt and unit of I is ampere. We have done it before. So what we can write it? The unit of resistance will be volt per ampere. Okay, and this is given a name. The scientist named it after himself as ohm. So what we write? 1 ohm. The symbol used for ohm is omega, is equal to 1 volt per ampere. Okay, so this is all about resistance and Ohm's law. Now, there's a term that is called conductance. Have you ever heard the term conductance? What is conductance? Very simple. You have understood resistance, right? The obstruction offered to the flow of current is known as resistance. Now, conductance, in a very simple language, it is defined as the reciprocal of resistance. The reciprocal of resistance. Okay, so what is conductance? The reciprocal of resistance. Now if it is the reciprocal of resistance, what will be the unit of conductance? The unit of conductance will be just the inverse of resistance. Unit of conductance. What is the unit of resistance? Ohm. So the unit of conductance will be ohm inverse. Okay, so this is about conductance. Now since we have discussed Ohm's law, also we should know how to prove Ohm's law, or how to write Ohm's law or show Ohm's law in a graph, in the form of a graph. Okay, so we will here discuss two types of graph, IV graph and VI graph. We will discuss about two types of graphs. Okay, IV graph and VI graph. Fine. Now let us see an IV graph. In an IV graph, the current I will be on the y-axis and the potential difference V will be on the x-axis. Now what have we studied in Ohm's law? We have studied that the current is directly proportional to the potential difference. So when a physical quantity is directly proportional to the other physical quantity, the graph shows a straight line passing through the origin. So if for a metallic conductor, we know that the ratio of V by I is constant. So for all values of V and I, so if we plot a graph for current against potential difference, we get a straight line passing through the origin. A straight line passing through the origin like this. Okay. Now let us find the slope of this graph. Slope. You must have done slope in mathematics, right? What is the formula for slope in mathematics? We write it, the general formula, y2 minus y1 by x2 minus x1. You can also write it as del y by del x. Change in the values of y by change in the values of x. Okay, now let us see in this graph what will be the value of slope. In the y-axis we have current, so we will have change in the values of current, that is del I, by x-axis we have potential difference del V. Now we know that V by I is resistance, right? So I by V will be reciprocal of resistance, 1 by R or 1 by resistance. Is it clear to all of you? Now let us see a VI graph. In a VI graph, V will be on the y-axis and I will be on the x-axis. Okay, again we will what we know is basically, be it a IV graph or a VI graph, we know that V is directly proportional to I. Hence what will happen if we plot a graph for all values of V and I, the graph will be a straight line passing through origin. Straight line passing through origin. Okay, obeying Ohm's law. So let us see the slope for this graph. We know it will be del y by del x. In the y-axis we have potential difference. So del V, in the x-axis current, del I. Del V by del I. So here you see the slope is giving you the value of resistance directly. Okay, so whenever you are given any question where you have a IV graph, then from the slope you will get the value of the reciprocal of resistance, which is also called conductance, right? Conductance. And whenever you are provided with a VI graph, directly from the slope you will get the value of resistance. Okay, now let us come to the limitation of Ohm's law. Limitation of Ohm's law. The limitation of Ohm's law is itself given in the statement. Okay, what does the statement say for Ohm's law? What the statement we read? We read that according to Ohm's law, the current flowing in a conductor is directly proportional to the potential difference applied across its ends, provided the physical conditions and temperature of the conductor remains constant. That means the limitation is if Ohm's law is obeyed only when the temperature of the conductor remains constant. So it will be obeyed only when the temperature of the conductor remains constant. So this is the limitation of Ohm's law. You may get it in objective questions in your board exams. Okay. Our next topic is ohmic and non-ohmic resistor. Now let us see what are ohmic and non-ohmic resistors. Here I have already written for you so that we can utilize it, we can do it in a lesser time. Okay. You see, we have two columns here for ohmic and non-ohmic resistors. First, let us see what are ohmic resistors. Ohmic resistors, it obeys the Ohm's law. It obeys the Ohm's law. So, any resistors which obey Ohm's law is known as ohmic resistor. By obeying Ohm's law, what does it mean? That the ratio of V and I will be constant for all values of V or I. Whereas in a non-ohmic resistor, it does not obey Ohm's law. That is, the ratio of V and I will not be constant. Okay. Second point, for ohmic resistor, the graph of the potential difference, that is V, versus the current, that is I, is a straight line, as we saw in our previous graphs. Okay, what was it? The whatever graph we drew, whether it was IV graph or VI graph, the graph was a straight line passing through the origin like this, right? If you have a V and I graph, the graph will be a straight line for ohmic resistor. Whereas for a non-ohmic resistor, the graph will somewhat look like this. It will not be a straight line. Okay, it will be a curved line. Okay, so you can see the difference between the two. Okay, the slope of the VI graph is same for all values of V or I at a given temperature. That means at a given temperature, if you calculate the slope of VI graph, since it's a straight line, you will get everywhere you will get the value of the slope same. For all values of V and I, you will get the same slope. Okay, whereas for this graph, for non-ohmic resistors, the slope of the VI graph is different at different values of V or I, even at a given temperature. That means even at a given temperature, for values of V and I, for different values of V and I, the slope will not be same. It will be different. Okay, now let us see the examples of ohmic and non-ohmic resistors. For ohmic resistors, all metallic conductors are examples of ohmic resistors. All metallic conductors, say for example, silver, copper, aluminium, etc., etc. These are all ohmic resistors. They follow Ohm's law. Now, what are the examples of non-ohmic resistors? Non-ohmic resistors, junction diode. Junction diode, you will be studying in class 11 about it. Junction diode, then LED, non-ohmic. Okay, then filament of a bulb, you must have seen in your house. You have all of you must be using bulbs in your house. So it has a filament. The bulb inside the glass case has a filament. That filament of a bulb is a non-ohmic resistor. Does not follow Ohm's law. Okay, so this is the difference between ohmic and non-ohmic resistor. Now let us do a few questions. I have here a set of questions for you. Question number 1. The figure below shows VI graph experimentally obtained in different cases. Okay, find out which graph is for ohmic and which one is for non-ohmic resistors. So you see there are a few graphs given. What we know about ohmic resistors, that they follow Ohm's law. That means if they follow Ohm's law, they'll be having a straight line. So these two are for ohmic resistors and C and D are for non-ohmic resistors. Okay. In our next question, we have a cell of 12 volt gives a current of 200 milliampere to an electric gadget. We have to find its resistance. So to do any sum in physics, first you write down all the data given to you. So what are the data given to you here? A cell of 12 volt. That means the potential difference of the cell is given to you 12 volt. Okay, and gives a current of 200 milliampere. That means current is given to you, I is equal to 200 milliampere. Okay, and we need to find its resistance, question mark. Okay, now you see the value of current is in milliampere, which is not SI unit. So first you need to convert it to SI unit. We know that 1 milliampere is equal to 1 milliampere is equal to 10 to the power minus 3 ampere. Okay, so that means 200 milliampere is equal to 200 into 10 to the power minus 3 ampere. Now we know the formula. We have V, we have I, we need to find R. According to Ohm's law, we know that V by I is equal to R. Therefore, R is equal to, we have the value of V, that is 12, and we have the value of I, that is 200 into 10 to the power minus 3. Okay, so when we calculate this, what are we going to get? 60 ohm. Okay, that is our answer. Okay, now see, in the next question we have calculate the potential difference required across a conductor of resistance 5 ohm to pass a current of 1.5 ampere through it. So what is given to us? We have been provided with the value of current, that is 1.5 ampere. We have been provided with the value of resistance, that is 5 ohm, and we need to find V. Question mark. According to Ohm's law, we know that V is equal to I into R. That means 1.5 into 5. That is equals to 7.5 volts. That is my answer. Okay, so these are few types of sums which we can get from Ohm's law. Okay, now let us see what are the factors affecting the resistance of a conductor. So our next topic is factors affecting the resistance of a conductor. Factors affecting the resistance of a conductor. Okay, so what are the factors that affect the resistance of a conductor? Altogether there are 4 factors. How many factors? 4 factors. Okay, what are the 4 factors? Number 1, the nature of the conductor. The nature of the conductor. Okay, number 2, we have the length of the conductor. Okay, number 3, the thickness of the conductor. Number 4, the temperature of the conductor. So what are the 4 factors on which the resistance of a conductor depend? The nature of the conductor, the length of the conductor, thickness of the conductor, and temperature of the conductor. Now how they depend on all these 4 categories? Okay, firstly we have the nature of the conductor. Different substances have different concentration of free electrons. Okay, different substances have different concentration of free electrons. Therefore, resistance of a conductor depends on its materials. For example, if you have silver, copper, lead, aluminium, all these have high concentration of electrons, so they offer less resistance. So they are called good conductors. But the substance like rubber, glass, wood, etc., they have negligible concentration of free electrons. So they offer very high resistance and are called insulators. So in short, what you conclude from here, we conclude that nature of the conductor, if the concentration of the free electrons in the conductor is more, then it has less resistance. So if the concentration of free electrons is more, the conductor offers less resistance. Okay. Now coming to the length of the conductor. How it is proportional? Always remember, resistance of a conductor is directly proportional to its length. That means if a conductor is of greater length, the resistance offered by the conductor will be more than that of a same conductor of shorter length. Okay, directly proportional. Next is thickness of the conductor. How it is dependent on the thickness? Resistance is inversely proportional to the area of cross section of the conducting wire. Okay, so that means the greater the area, the lesser the resistance. The greater the area, the lesser the resistance. Inversely proportional to each other. And finally, temperature. The resistance of a conductor increases with increase in temperature. Always remember, resistance of a conductor increases with increase in temperature. Increases with increase in temperature. That means they are directly proportional to each other. Okay, greater the temperature, greater will be the resistance. Okay. Now let us see a graph where we see the dependencies of resistance on temperature. That means for this one. Okay. Let us see a graph. Here a graph is given to us. It's a VI graph. V in the y-axis and I in the x-axis. V, potential difference in the y-axis and current in the I-axis. Okay. This is the straight line. This is a straight line, the slope of which will give the resistance, okay, at temperature T1. And the slope of this will give the resistance, and this is maintained at temperature T2 in such a way that T1 is greater than T2. That means the temperature 1 is greater than the second temperature. Now if you see the graph, you see the slope of graph A, the straight line A, the slope of the straight line A, which is at a temperature T1, is steeper. That means it will have a greater slope, and if it has a greater slope, it will have a greater value of resistance. Understood? So again you see this one, the straight line B. In straight line B, it is less steep. It is if you compare A and B, you see the slope of this is lesser than that of A. The slope of B is lesser than that of A. So what we can say, that at a lesser temperature the resistance is also less, at a greater temperature the resistance is also more. So these were all the 4 factors on which the resistance of a conductor depends: nature, length, thickness and temperature. Okay, but from nature what we concluded? We concluded that greater the concentration of free electron, lesser will be the resistance. Now for length, resistance directly proportional to length, greater the length, greater the resistance, and it is inversely proportional to A. That means greater the area, lesser the resistance. And finally it depends on temperature. It is directly proportional to temperature. Greater the temperature, greater will be the value of resistance for a particular conductor. Now, our next topic is specific resistance. Specific resistance. To understand what is specific resistance, first we will see whatever we have just done, the dependencies of resistance on various factors. So what did we do? Experimentally we found we got two observations from the previous topic. I'm taking two observations. Observation number 1, the resistance is directly proportional to L. And observation number 2, that was resistance is inversely proportional to area, or we can also write it as resistance inversely proportional to area. Area of a cross section of a wire is pi r square. Now if I write them together, can I write it like this? R is directly proportional to L by A. From here we get both R directly proportional to L and R inversely proportional to A. Now again, if I remove this proportional sign and replace it with an equal to sign, I told you we always get a constant. So we'll have a constant here. Right? This constant is given the name of specific resistance. So this constant is called specific resistance. Okay? Specific resistance is denoted by the symbol rho. R-H-O. Rho. Okay? So how can you write it? R is equal to rho L by A. Or if you want to make rho the subject of formula, how you're going to write? Rho is equal to R, A will go there, A by L. So what we have? Rho is the specific resistance or resistivity. We can also call it resistivity. Okay, R is the resistance, A is the area, and L is the length of the conductor. Okay, so this is clear to you. Now let us see what is the unit of specific resistance. Unit of specific resistance. Okay, so let us see what is the unit. Unit of specific resistance. We have already seen the formula. So what does the formula says? The formula says rho is equal to R A by L. R A by L. So if we find the unit of rho, it will be unit of R into unit of A by unit of L. Okay, so what is the unit of R? Ohm. What is the unit of A? A is area, so meter square. What is the unit of L? L is length, so meter. This meter will get cancelled out, so you are left with ohm meter. Therefore, unit of rho is ohm meter. Okay, so this is the SI unit of specific resistance. Now, specific resistance, as I told you, it is also called resistivity. It is also called resistivity. Now, just as we have resistance and the reciprocal of resistance is conductance, similarly, the reciprocal of resistivity is conductivity. The reciprocal of resistivity is conductivity. Okay, conductivity is denoted by the symbol sigma. Okay, so what we can write? Sigma is the reciprocal of rho. That means the conductivity is equal to the reciprocal of resistivity. The conductivity is equal to 1 by resistivity. So if it is equal to 1 by resistivity, what will be the unit? It will be equal to 1 by unit of resistivity. And what is the unit of resistivity? Ohm meter. So the unit of conductivity, unit will be ohm inverse meter inverse. Okay, you can also ohm inverse and meter inverse. Now, the last topic for current electricity part 1 is superconductors. Have you heard about superconductors? What is superconductors? You don't have to study superconductors in detail because we don't have its use in our daily life, because we cannot obtain this superconductors. Okay, it's quite difficult. Why? First, let us see the definition of superconductors. What is superconductor? A superconductor is a substance of zero resistance, at a very low temperature. What does this mean? I have already told you, any metal, be it any metal, no metal can be free of resistance. Okay, so basically there are no metal which has zero resistance, but there are metals which at very low temperature show zero resistance. For example, metal like mercury. Mercury is not a superconductor, but mercury at or below 4.2 Kelvin will act as a superconductor, because below 4.2 Kelvin the resistance of mercury will be zero. Similarly, lead below 7.25 Kelvin. Okay, below 7.25 Kelvin it will offer zero resistance. Okay, another example is niobium. Again, this is also at a very low temperature, below 9.2 Kelvin. It will act as a superconductor. Okay, so such low temperatures are quite difficult to achieve, right? It is very difficult to achieve, in fact. So they can be very useful if it is possible to obtain it at room temperature. Then because if we need a good amount of current, the resistance offered by them will be zero, so we can get that current. But it is not possible to obtain them at room temperature. They occur at a very low temperature.